In the previous video, we have discussed about the algebraic structure, in which we discussed group, uh, which is a combination of the set as well as certain operator. A particular set and the operator can be called as a group if it satisfies four different properties, and those properties are: the first property is the closure property, associativity, as well as the identity and the inverse. We also discussed about the subgroup and order of the group, finite group, cyclic group. We have discussed. So, in algebraic structure, besides having group as one of the structure, we have two more structures. The second structure is called ring, and the third structure is called field. So, before we go into the ring and the field to discuss about that, first of all we have to find out the order of the element in a particular group. So, the order of any element of a particular group can be represented as order A, and it is can be find out that it is a smallest integer n, and if such that a to the power n is equal to e, where e is the identity element of the group. So, n will be called order of A if a to the power n is equal to e. Now, here you have to consider a to the power n. Of course, it seems to be an exponential, but it depends upon the operator on which it is being defined. Suppose if the operator is addition operator, then a to the power n means a plus a plus a up to n times. But if it is operator is multiplicative, then it means a to the power n is equal to a into a to n times. So, this is the only difference. So, a to the power n is should be equal to e. If the addition operator is there, then a to the power n should be equal to e. One more thing, if the operator is additive, in that case identity element in the additive operator is 0. And if the operator is multiplicative, then in that case the identity element is 1. So, this we already know. So, how to obtain the field, how to obtain the order of an element? That will be the smallest integer n, such that a to the power n is equal to the identity element. So, let us take an example. Suppose if group is given as G is Z6 plus. So, Z6 contains how many elements? 0, 1, 2, 3, 4 and 5. There will be 6 elements from 0 to n minus 1, where the value of n is 6. So, 0 to 5. So, we have to find out the order of each of the elements 0, 1, 2, 3, and we also know that the identity element in this particular case, since the operator is addition, the identity element is 0. So, if we want to get the order of 0, so 0 order will be represented by 0 to the power n, such that we should get the value equal to 0. So, 0 will be added by how many times? If 0 is added 1 time, if the 0 is added 0 time, if the 0 is added 2 times, whatever is the smallest integer, that will become the order of that group. So, as far as 0 is concerned, the order of, if n is equal to 0, then 0 to the power n means 0, this will be equal to 0, which is the identity element. So, it means order of 0 is 0. Let us check order of 1 to the power n. What you have to do? 1 to the power n. So, what will be the value of n, such that this value 1 to the power n should be equal to the identity element, which is equal to 0. So, we can take, if I consider that suppose n is equal to 1. So, in that case n is equal to 1. So, 1 to the power 1 is equal to 1. So, 1 cannot be the order of element. So, what will be the order of element? If we take n is equal to 2, then the order of element will be 2. But the order of 1 will not be, because it will be equal to 1 plus 1, that is equal to 2, and this 2 is not an identity element. So, 2 cannot be the order. So, what will be the order? if I consider n is equal to 5, sorry 6, if consider n is equal to 6, then 1 to the power 6 will be equal to 1 plus 1 plus 1 plus 1 plus 1 plus 1, that is equal to 6, and the mod value is given 6, so 6 mod 6, it is equal to 0. So since 1 to the power 6 is equal to 0, so 6 is the order of 1. Similarly, order of 2 will be 2 to the power n. 2 will be added how many times, so that the resultant will be equal to the identity element. So 2 is added, 2 plus 2 plus 2, that will be equal to 6, and 6 mod 6 is equal to 0. So it means order of 2 is 2 to the power n, that is 2 to the power 3. So order of 2 is 3. Similarly, order of 3, 3 to the power n. How many times 3 will be added, so that the resultant will be equal to 0? So 3 plus 3 is equal to 6, and 6 mod 6 is equal to 0. So order of 3 is 2, 3 to the power 2. So order of 3 is 2. Similarly, order of 4. What will be the order of 4? So 4 to the power n. What you have to do? You have to find out the value of n, smallest value of n, such that 4 to the power n, if 4 is added n times, the resultant should be equal to, so if 4 is added, how many times? Here the mod value is 6. So if 4 is added with 4, it will be 8, not 0. If 4 is added 3 times, so it will be getting 12, and 12 mod 6 is equal to 0. So it means 4 to the power 3. So it means order of 4 is 3. So order of 5, 5 to the power n. If 5 is added how many times? If 5 plus 5, 10, for 5, 15, plus 5, 20, plus 5, 25, plus 5, 30, and 30 mod 6 is equal to 0. So order of 5 is 1, 2, 3, 4, 5, 6. Order of 5 is 6. So order of 0 is 0. Order of 1 is 6. Order of 2 is 3. Order of 3 is 2. Order of 4 is 3. And order of 5 is 6. Let us take another example. This is the example which is in which we have addition operator. Let us take another example in which we will be taking the multiplicative operator. And then we will try to find out what is the order of the elements in that group. So next example is G is equal to Z10 star multiplication. We know what is Z10 star. Z10 star contains those elements which are co-prime with Z10. So what Z10 star contains? 1, 3, 7, 9. Only 4 elements. And the operator is multiplicative, so the value of E, identity element, will be 1. Now let us find out order of 1, 1 to the power n. So 1 to the power n, if I consider n is equal to 1, then 1 to the power 1 will be equal to 1, and that is getting the identity element. It means order of 1 is 1. Order of 3, that will give you 3 to the power n. So 3 to the power n. So, and the mod value is 10. So we have to select the smallest integer n. If we select 1, n is equal to 1, then 3 mod 10 will be equal to 3. It is not coming 1. So 1 cannot be the order. If we consider 2, 3 is a 9. 9 mod 10 will be equal to 9. It is not coming 1. So let us take 3. 3 to the power 3. It will be equal to 27. 27 mod 10 will be equal to 7. It is not coming. So it cannot be. So let us select 3 to the power 4. Suppose n is equal to 4. So that will become 81. And 81 mod 10 will be equal to 1. So order of 3 will be 4. Order of 7, 7 to the power n. If 7 is taken 2 times, it will become 49. 49 mod 10 will be equal to 9. If we take another 7 cross 7, 4 times, so that will be giving 9 and that will be giving 9. So 9 into 9 mod 10, that will be giving 1. It means if 7 is multiplied 4 times, it means if the value of n is equal to 4, then it is going to get the identity element. So the order of 7 will be 4. Order of 9, 9 to the power n. If we multiply 9 to 2 times, that is n is equal to 2, then it will be 81. 81 mod 10 is equal to 1. So order of 9 will be 2. So order of 1 is equal to 1, order of 3 is equal to 4, order of 7 is also 4, and order of 9 will be 2. So in this way, we used to get the order of element. Pause karna. The second algebraic structure, that is ring. A ring is denoted as R, which contains a set and 2 operators. This ring is an algebraic structure with 2 operations. It means in group we apply 1 operator on the set, but a ring has 2 operators on the set. The operators are represented as star and the rectangle. These are the 2 operators. Now with this 2 operator, this particular set can be called as a ring with if it satisfies certain property. That property is, with the first operator, it must satisfy all 5 properties to be called as a abelian group. A group can be called abelian group if it is commutative also, meaning thereby besides 4 basic properties, that is closure property, associativity, identity and inverse, if the group is also satisfying, if the operator is also satisfying the commutative property, then that group is called abelian group. So a set along with 2 operators can be called as a ring if the first operator is satisfying all 5 properties of abelian group, and the second operator should satisfy first 2 properties of a group. First 2 property means closure property and the associativity. And besides these 2, the second operator must be distributive over the first operator. It means there are 3 conditions. The first condition is the first operator must satisfy 5 properties of abelian group, that is closure, associativity, inverse, identity as well as commutative. And the second operator must satisfy the closure property as well as associativity, as well as both the operator should satisfy the distributive property. If all these 3 are satisfied, then a particular set along with these 2 operators can be called as a ring, otherwise not. So the third property which I'm not going to write anything. I have already explained that this should satisfy all 5 property and this should satisfy first 2 property. And besides that, the second operation must be distributive over the first operator. What does it mean? It means that if A, B and C are the element of the set, then it means that A, B star is equal to A, B star, A, C, and A star B operator C is equal to A star B operator A star C. This is the distributive property. So this, if all these properties are satisfied, that set along with the two operator can be called as a ring. Then the next one is commutative ring. What is commutative ring? If for the second operation, if the second operator is also satisfying the commutative property, then that ring will be called commutative ring. And if you want to take commutative ring, is that in which second operator is satisfying commutative property. Now let us give you an example of a ring Z plus and a star multiplication is an example of a commutative ring. It is an example of a commutative ring. Now field. This is all about commutative ring. Field. A field F, as group is represented by G, ring is represented by R, field is represented by F. So what is F? F has set having certain element, finite number of elements, and having two operators, is a commutative ring. Is a commutative ring in which second operation satisfies all five properties defined for the first operation, defined for the first operation, except that identity of first operation, identity of the first operation sometimes zero element possibility hai, zero element has no inverse. So field is actually a commutative ring is called field, but with the condition that the second operation should also satisfy all the five properties which are being satisfied by the first operation, except that if the first operation, whatever is the identity of the first operation, if it is 0, then it will have no inverse element. If this condition is true, then that set along with the two operator can be called as a field. So you can distinguish now what is group, what is ring, and what is field. Group contains one set and one operator. Ring contains one set and two operator, with the condition that the first operator will be satisfying all five properties, second operator will be satisfying only first two property, along with it should be distributive. The third one algebraic structure is the field, in which we have one set, two operators, and both the operators should satisfy all the five properties, except that the first operator, whatever is the identity element of the first operator, it may be possible that it will not have any inverse. So that is called field. So in cryptography, why we are studying all these things? Actually, we are more concerned about the field in cryptography, and for working with the field, it is necessary that what is group and what is ring, then only you can uh, go for the field, understand the field. Until unless you don't know about the group, you don't know about the ring, you cannot understand what is field. So in field we have finite field. Finite field is a kind of field which has finite number of the elements. Normally fields are of infinite order, but finite fields are extensively used in cryptography. That is why we are more interested in the finite field. And finite field, as I told you, that it has finite number of the elements, and that is used in the cryptography. So this finite field, there was one mathematician, Galois. Galois showed that for a field to be infinite, for a field to be finite, the number of elements should be, Galois has the hypothesis based on which it has given that a field can be called as a finite, it will have finite number of the elements. uh, Field to be a finite, the number of elements should be p to the power n, where p is a prime number and n is a positive integer, where p is a prime number and n is a positive integer. So the finite field is actually it is represented designated by Galois. So finite field is also called Galois field, and Galois field is represented as GF p to the power n, where p to the power n is number of elements present in that particular field. So what is stands for GF stands for Galois field having finite number of the elements, and that elements will be p to represented by p to the power n. So now GFP field, meaning thereby if we consider that n is equal to 1, then that field GFP to the power n will be represented as GFP. So what GFP represents, when n is equal to 1, we have GFP field, and this field can be a set represented by ZP, that is from 0, 1 up to p minus 1, with two arithmetic operator, that is addition and multiplication. Each element has additive inverse and the non-zero element has, and all non-zero elements has multiplicative inverse. So GFP is one of the abstraction of GFP, Galois field p to the power n, where the value of n is equal to 1. It contains a set which is ZP, that is from 0 to 1, 0, 1 up to p minus 1, with two arithmetic operators, addition as well as subtraction, where each element on this particular set will have its additive inverse, and each non-zero element, besides the zero, rest of the element must have multiplicative inverse. So let us take an example. Suppose we want GF. Now, suppose we are talking about GFP. Suppose P is equal to 2, because P is 2 is a prime number. So, suppose we take the example GF2. So, what about the GF2 field? What will be the GF2 field? Now, this GF2 field will have two elements, 0 and 1, and the operators which are defined are addition as well as multiplication. So, how it will work? If we talk about 0, 1, 0, 1, multiplication 0, 1, 0, 1, and then we have inverse, additive inverse, and then we have a multiplicative inverse 0, 1, 0, 1. So, let us find out what happens. 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 will be 1, and 1 plus 1 will be equal to 0. 0 multiplied by 0, it will be 0, it will be 0, and it will be 1. What will be the inverse? What is the inverse of 0? Additive inverse of 0. What element you will add in 0 to get 0? So, naturally it will be 0. And what will be the inverse of 1? What you will add in 1 so that you will get the identity element, that is 0. So, it will be 1. Because we know 1 plus 1 mod 2. 1 plus 1 is equal to 2, and you take mod 2, that will be coming as 0. What will be the multiplicative inverse? 0 will have no inverse, because it has been stated in the definition that non-zero elements should have inverse, multiplicative inverse, but the zero elements will not have any multiplicative. So, we will leave this, and what will be the inverse of 1? What number you multiplied in 1 so that you will get 1, so that will be equal to 1. So, you see, the analogous operations which we have studied in the binary, in the form of a binary operation. So, what happens, what seems it to be? If I am talking about GF2 field, if we are talking about GF2 field, addition operation as well as the subtraction operation is actually all in GF2 field. Addition and subtraction is similar to XOR operation. You can see, if the elements are same, the result is 0. If the elements are different, the result is 1. If the elements are different, the result is 1. If the elements are same, the result is 0. So, addition as well as subtraction is similar to the XOR operation. And what about this multiplication and division? The multiplication as well as the division is similar to AND operation. So, let us take another example. But this is applicable, this addition and subtraction is similar to XOR operation if we are talking about GF2 field, and multiplication and division is similar to AND operation if we are talking about GF2 field. If I am taking another example, suppose I am taking the example of GF5, then let us see what happens. So, it will have, the number of elements will be changed, it will be 0, 1, 2, 3, 4, and the operator will be addition as well as multiplication. So, let us take first the plus operation, 0, 1, 2, 1, 2, 3, 4, 0, 1, 2, 3, 4. What will we be getting? 0 plus 0 is 0, 1, 2, 3, 4, If 1 is added, 1, 2, 3, 4, and then it will be 0. Why it is 0? Because 1 plus 4 is equal to 5, and 5 mod 5, because it is of the modulus is 5. So 5 mod 5 is equal to 0. Similarly, 2 plus 0, 2, 2 plus 1, 3, 2 plus 2, 4, 2 plus 3, 5, 5 mod 5, 0. 2 plus 4, 6, 6 mod 5 is equal to 1. 3, 0, 0, 3, 1, it will become 4. 3 plus 2, 5, 5 mod 5 is equal to 0. 3 plus 3, 6, 6 mod 5 is equal to 1. And 3 plus 4, 7, 7 mod 5 is equal to 2. And 4, 4 plus 0, 4, 4 plus 1, 0. Why? Because 4 plus 1 will be 5, and 5 mod 5 will be 0. 4 plus 2, 6, 6 mod 5 is equal to 1. 4 plus 3, 7, 7 mod 5 is equal to 2. 4 plus 4, 8, 8 mod 5 is equal to 3. Let us take the multiplication. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. If we multiply 0 with any element, we will be getting 0. If we multiply 1 with 0, 0, 1 is multiplied, so we will be getting same element. If we multiply 2 with 0, it will be 0. Any number, it will be 0, 0. 2 multiplied by 1, 2, 2 multiplied by 2, 4, 2 multiplied by 3, 6, 6 mod 5 is equal to 1, and 2 multiplied by 4, 8, 8 mod 5 is equal to 3. 3 into 1, 3, 3 into 2, 6, 6 mod 5, 1, 3 into 3, 9, 9 mod 5, 4, 3 into 4, 12, 12 mod 5, 2. 4 multiplied by 1, 4, 4 2s are 8, we will get 3, 4, 3, 12, 12 get 2, and 4, 4, 16, we will get 1. So, this type of elements we will be getting. And what about additive inverse and the multiplicative inverse? Let us check. First of all, we will go with the multiplicative inverse. Sorry, additive inverse. A, and what will be the A inverse? 0, 1, 2, 3, 4. What will be the additive inverse of 0? Of course, it will be 0. Additive inverse of 1, which element is added into 1 and then take mod 5 so that it will become 0, so it will be 4. Additive inverse of 2 will be 3, additive inverse of 3 will be 2, and additive inverse of 4 will be 1. Why it is so? Because 4 plus 1, 5, 5 mod 5 is equal to 0. 3 to 5, 5 mod 5 is equal to 0. 3 to 5, so in this way the additive inverse will be. Let us check multiplicative inverse. A inverse. 0 will not have any inverse, multiplicative inverse. 1 will have its multiplicative inverse. What element is multiplied in 1 so that you will get the result 1? So that will be 1. 2. What number should be multiplied by 2 so that when you take mod 5, that will be 3? It should be equal to 1, because 3 into 2, 6, and 6 mod 5 is equal to 1. 1 is the identity element of the multiplication. Similarly, what if if inverse of 2 is 3, so naturally the inverse of 3 will be 2. And what will be the inverse of 4? If 4 is multiplied by 4, that will become 16, and 16 mod 5 will be 1. So the inverse of 4 will be 4. So what does it suggest? That every element is having closure property, satisfying closure property. If it is satisfying, it is also satisfying the associativity and the associativity. Every element is having additive inverse, and every element is having multiplicative inverse besides the 0 element. So this is all about the GF2 field and GF5 field. But we are also more concerned with GF p to the power n. So we will discuss GF further, the field which is GF p to the power n in the next video. Thank you.